Welcome to this morning's Tech Talk. Today, we're very happy to have Sanjeev Khudanpur from Johns Hopkins University come here to talk about content-based image and video retrieval using HMM. Sanjeev got his PhD from University of Maryland, and then has been at Johns Hopkins University as an assistant professor. Sanjeev is a world expert in language modeling, and he has been using language modeling techniques in many different areas: speech recognition, machine translation, and natural language processing in general. And today it looks like maybe Sanjeev is broadening his application area to a very different area. And this, Sanjeev has graciously agreed to allow Google to post the video on the externally on Google Video. So if you have, if your question is related to kind of Google products and so on, that's not in a public domain. Can you please ask these kind of questions after the talk, or join us at lunch right after this talk. Without further ado.
Thank you, Rika. Thanks for coming in. This is indeed an area where I haven't done much before, and I'll tell you very shortly that I got into this content-based video retrieval only a year and a half ago, thanks to a bunch of very smart people who came to Hopkins in the summer to do some research on it, and I just latched onto them and found something interesting. And like with a lot of research, I looked at their problem and said, hey, wait a minute, I can do that. And sure enough, it turned out to be a lot harder than I thought, but on the other hand, I got to try something new, so I'll tell you a story about that. And then please feel free to interrupt anytime with questions. I'm usually used to being heckled by my colleagues and students, so it won't be a problem. Especially if there's something which is not clear on the slides or what I'm saying. So it's better to spend your time knowing what I'm saying rather than waste it. And if it's too boring, you can So the image and video retrieval problem, it's I suppose I'm preaching to the choir when I talk about it at Google. It's essentially, you want to provide, it's about providing access to images and video based essentially on textual queries, because it's very often hard for people to provide their information needed in any other way. They're typically explained in words or something. And when it comes to things like television broadcasts and so on, people have shown over time, I don't know how many of you have seen the compact speech board. You can get fairly decent access to news-style videos just by doing speech recognition and doing search of the transcripts. And then there are other cases. For example, if you're looking for images on the web, I'm sure you guys very well know how to do images there. It essentially looks for the URLs or the anchor text and so on. And that's a pretty good tool for figuring out what to do. I'm interested in the other kind where there is no such metadata visible, but you really have to look into the image to see what is in it in order to find the message. And this could be things like surveillance imagery from unmanned or what is a very interesting setup is raw footage. So oftentimes when you see a 30-second or 1-minute news clip, there are typically several minutes or even hours of video behind it, the raw footage. And then the production team looks through it and finds it and puts it together, and there's usually a narrative overlaid on it. So if you're looking at the original footage, it's very hard to search in it because there's often no audio to go with it at all. So those are the kind of things which are interesting, and people have been working on this. And I sort of got introduced to this problem, like I said, a year and a half. So what have people done in this domain before? So what happened is the big problem was how do you sort of do research, how do you show your results? You need common data sets. So a lot of people have published on something called the Corel images. So the Corel images, these are like stock photographs from people who sell Corel Draw or something. And they have CDs with about 100 images each, and they sell, I don't know, anything from 50 to 700 CDs. And These are not easy to get your hands on because often you have to buy the software to get the picture. And I couldn't even find the software, but I got these images courtesy of some colleagues at Berkeley who sort of figured out some way of giving us part of these images. I'm not quite sure what the rules are about, but I don't ask. Don't ask for policy. And then these photographs are captioned manually. And you'll see examples. So for example, there are 100 pictures about polar bears, or bears in general, bears of woods, bears of snow. And then there are another 100 pictures of flowers, another 100 pictures of horses, and so on and so forth. And so these are groups of pictures. And people often, what they do is they sort of make a training test partition, put 90 images of training test. And I'll show you how that can sometimes be problematic. But I think the way these things have been done, the training and test set are too much like each other. And so people often get dramatically good results on this data set, which don't then scale up to other tasks. So when the IR community started looking at it some years ago, they essentially did what the IR community has always done. They got hold of list and said, okay, you create for us a standard benchmark test, and we'll all have identical training testing conditions, and we'll see what happens. So the main results I'm going to give you are on this MIST video TREC, or TRECVID video retrieval task. So this is very much modeled after the MIST ad hoc task. I'm assuming, by the way, everyone's familiar with the MIST ad hoc task? Yes? Okay, so the way it works is, I see some people going this way. So the way it works is, like, there's a huge collection of documents, and they have various versions of it. Some of them involve newswire stories, some of them involve 300 pages. And typically they get information analysts, retired information analysts for the CIA or NSA, to come in and say, okay, think of something you're looking for. And somebody might say, yeah, I'm interested in finding out something about this disease because my brother-in-law has it, and I want to figure out what it does. And so they say, okay, sit down and formulate your query. And they have a certain template saying, give us a couple of keywords, give us a one-sentence description, and then give us a little bit of a narrative saying, I want to know the causes of the disease and the symptoms. I'm not interested in, like, the biopathology of it or so on and so forth. I want it from a diseased person or a patient's perspective and so on. And then the search engine's task, and, like, typically 60, 80, 100 people participate in this when it's done. They all try to use this information needs specification and try to get documents from this collection. And post hoc, after everybody has run their systems, MIST puts together everybody's top few retrieved documents. And the person who was looking for the information then goes in and actually makes assessments, saying, yes, this document is useful to me, or this is not. So there's a real information need, there's a real user. It's not too far removed from what might actually happen next time. So that's the model. And so they did the same thing. They got hold of news broadcasts, and they had already got hold of it before because they were doing spoken document retrieval earlier. So there are several hundreds of hours of video from news sources, CNN, ABC, CNBC, Corel brands, and the other, and so on and so forth. So some talk news analysis and talk, and some just straight news. And last year they added Arabic and Chinese broadcasts because the US government is interested in it. So think of a whole bunch of video, of commercial video quality, typically VHS quality. And then that's what they said. They said we'll do this ad hoc task just like the document. So somebody will say, give me shots of aerial views of buildings and roads. Or one of them I think said something like, give me shots of floods. So show me pictures, aerial pictures of a flooded city or a flooded neighborhood and things like that. And so these were visual queries now instead of the usual text-based information. And they divided up the task into 3 component parts. One of them is just shot boundary detection. If you're running video, when do you know that the camera shot has changed? And they have a certain technical definition of shots. This is not what I'm going to talk about. We also have the full ad hoc retrieval the way I described it. I'm not going to talk about that either. I'm going to talk about this in the middle. NIST calls it high-level feature detection. And people who have worked in object recognition will think of this as object recognition. Find me images with cars. Find me video with someone playing tennis. Find me video with a truck passing by. I want the truck coming from in front and going by behind me in front. So those are kind of things that people specify in this task. And what is available through NIST, 2 years ago they created a collection which had about 44,000 keyframes. And keyframe is sort of a middle frame in a shot. Like those of you who know MPEG will know this would be typically an iframe or something. And then they have a similar collection held out for testing purposes, and then last year they came up with another collection, slightly bigger, 75,000 people training, including a fairly large data set. How do you measure things? Again, the community took the attitude that we're going to evaluate this like ranking. So if I have a whole collection of images and I say give me images with cars, they give me a ranked list. And at every position where you give me a video clip of a car, I'm going to see how many above that point have cars. So if the first one's a car, the precision at that point is 100%. The second's not a car, the third's not a car, the fourth one has a car. So at that point, the precision is 50% because 2 or 4 have cars. Yep.
How many slides do you have?
22.
All right.
Okay. Do you want me to speed up, slow down? Speed up.
Yeah, we're not going to make, at this rate, we're not going to make it.
All right, good. So we'll speed up. So this is the usual stuff, and the ranked images are labeled, and sort of you measure precision recall. Hopefully you all know what this is. It's just an average over various levels of recall, and averaged over many queries, and this is the usual track measure. And 1 means you're perfect retrieval, all the relevant things on top. 0 means all the relevant things on top. And high is the So these are typical queries used in this high-level feature detection task. So they have, and some of these I really don't understand. So they have things like, they had this in 2003, new subject face, new subject monologue. I have no idea how they expect the image to tell you which is which. Perhaps, if you look at the length of the video, maybe. But in the things I'm doing, I have no way of telling these two. In 2005, they revised their concept list a little bit. And I'll call them concept, list calls them features. So now they have features like sports in progress, views of mountains, waterscapes, and so on and so forth. So this is the typical inventory of features that you want to detect in the video, right? Okay, so far so good? So when I walked into this problem, it was June of 2004. And for those of you who don't know, every summer in Johns Hopkins we have a summer workshop where we get about 10 people per team, 2 or 3 teams working on interesting research problems for 2 months. And these are typically people drawn from all over the world. Half of them are researchers, the other half are students and so on. And so there was a team headed by Iyengar at IBM, and there were a couple of other people. Who was at the time, I think at CMU in Wilkin, and Nock, who was at Amherst. So these are people who have worked on this problem before, especially on the Corel images. And I'll show you some results from both these groups on the Corel images. So they had worked on it. And they had taken a couple of different approaches. The approach that Pinar, and this is work that started probably at Berkeley with David Forsyth and a couple of other people, was to take the image, segment it into regions, and each image region sort of quantize it for whatever visual properties you're looking for into some discrete vocabulary. So what happens is the image now looks like a bag of words. And its caption, which comes in the Corel vocabulary of the image, also looks like a bag of words. And so they said, let's just treat it like a translation problem. One language is the language of blobs, as they called it. So these blobs were discretized representations of image regions. And the other language is the language of words. And they just trained up a standard machine translation system. And it seems to do fairly well. And this paper in particular got, I believe it got the best paper award at ECCD or something. It's a fairly decent system, not bad. And of course, you train on a bunch of training images and you roll out some. And I think in the case of the Corel, this particular paper, they had 4,500 images of training, 500 testing. Now, these guys from UMass, they took a slightly different approach. They said, we'll treat this like a cross-language IR problem. So the query is in words, and the documents are in blobs. So it's like English-Chinese, and they pulled out some ideas they had been using for cross-language IR. Again, the same thing, they discretized the images. And they essentially said, each image in your training collection, which happens to be annotated, so let's say big J is the size of your training collection, or one image in your training collection. We'll treat this as a sample whose relevance or closeness to the test image, the image that you want to annotate automatically, is given by this row. And this, for example, in case of cross-language IR, would be based on some sort of translation dictionary. So you'd say, if this red is Chinese and blue is English, I have an English query to a Chinese document. Oh, sorry, this would have to be a Chinese query to an English document. So here's the similarity between the two documents. And then I simply look at what the concepts are known to have been present in the document, in the image that is labeled, that's J. And I'll just use the presence of concepts in J times the similarity of J to I to come up with what might be present in I. Right, so they call this the relevance model. And in particular, this similarity can be computed using any kernel. And in fact, if you want to get away from this discretization of the image regions, you can simply model the image features as continuous value vectors and stick a Gaussian instead of a capital field, right, in place of capital. So they did this, and again, this meets with some reasonable success. So this was the state of the art as we went into the problem in summer before, right? So this is what we proposed, and when I say we, I mean Pavel Ursing, who was at the time a grad student in the University of West Bohemia in Czech Republic, and I. And we said, let's think of the image as a stochastic process, which is generated by an underlying hidden process, and the hidden process takes values in this vocabulary of words, labels. So if I'm going to caption an image, and let's say my caption vocabulary has 500 words, it could be very large. And I simply think of a Markov chain that takes values in this set. And if I'm given the caption of the image, I know which states were visited out of the 300 possible states. So this particular image was captioned with building, sky, outdoors, and car. By the way, this is what comes with the data set. So for example, they didn't bother to label the person in the image. You just have to live with it. And, and then you basically think of the image as being stochastically generated by this underlying process. And to not to assume that the process is independent, we can put in some transition probability. So it's a fairly simplistic model. And in fact, if you think really carefully, this does look like a Gaussian mixture model if I decide to model the emission densities as Gaussians. So close enough. All right, so a quick note on what these visual features are. In other words, what is being observed in this image, right? So one of the decisions we made is we just said we'll segment the image not by regions, but into fixed length blocks, 35, 50 by 50 blocks. And then visual features are extracted from each block, and these visual features were things like the color moments. And for reasons that I'm not an expert at, I can just tell you they were moved into this LAB color space where apparently perception is more linear in the value of the colors and so on. And essentially it says the mean of the red, or the L-ness or the A-ness or the B-ness of the little block. If you're thinking RBG, it would be the mean redness, blueness, greenness of the block. And then the variance and so on and so forth. So you extract sort of visual features. And so for example, there are 3 L, A, and B components, and each of them have 4 moments, so this would be a 12-dimensional vector of real value things. Right? And similarly, there was we extract oriented edge histogram. So you have a little filter that says, is there an edge in this direction? And the output of the filter is quantized to 4 or 8 levels. And so you say the strength of an edge in this direction in this little sub-image is so much. It's 1 through 8 or 0 through 7. And then there's another filter which says, is there an edge this way? Is there a vertical edge? Is there a horizontal edge? And you get a bunch of edge strengths. And that's another vector, and that's this vector. And then similarly, you look at the texture of an image by asking yourself, how often are 2 neighboring pixels in a grayscale version of the image the same level? And that gives you some sort of, so all of these are vector valued quantities, and you just concatenate all of them and get like an 80-dimensional vector. So that's the feature extracted out of each little sub-image. And again, we didn't do extraction of these features, we just got them from our colleagues at IBM, Iyengar, who happened to be at the summer workshop, and he happens to know how to do some of these things. Yeah.
This might be a dumb question, but in the previous slide where you had the example of the car and the sky and the guy,
yeah.
How would the processing, how would the outcome of classifying this image different if it had been taken in infrared at night? So the sky was not blue and all that sort of stuff.
The system we have right now, it would just hope that it had seen enough infrared images in its training that it would recognize it. So in that sense, it's fairly dumb.
All right.
It's just a statistical matching kind of an attitude towards the problem. Yes, I agree. It's not doing anything even close to object recognition. And in fact, that's partly, this is one of my criticisms of some of the other works that I just mentioned about, like in the Corel drop pictures. I've seen people, and Stefan here will tell me it's true, that people show images where the computer says Scottish farm, as if there is some hope in hell that this computer actually recognizes a Scottish farm and knows how it's different from an English farm.
Well, thinking ahead, since you're not doing image analysis,
yeah.
but you're making inferences about an image based on its annotation.
Right.
What one wonders is that if you did enough of that, right, enough well-annotated images, is there a theory or is there some sort of unstated goal behind your research that if you did enough of analyzing annotated images, then when you received an unannotated image and you tried to do some feature extraction, you could look at the statistical properties of the feature extraction, match that up with all of the annotated feature extractions from the other one, and then be able to reason about the unannotated image. I'm wondering if that is a goal that you see beyond the current research, or if the current research focuses only on the statistical properties of annotated images.
Right. That precisely is the goal. And let me maybe articulate it in slightly broader or vaguer terms. I come from a background in speech recognition. I worked on it for 6 or 7 years before I got into this problem. And there we've seen this, that like you get a number of speakers who speak and somebody transcribes it and annotate it. And then you do want to go and recognize a new speaker, typically under different acoustic conditions. And as you go further and further away from your annotated speech, the performance gets worse and worse. So if it's the same speaker, you're doing great, especially with the same microphone. You change microphones, you do worse. You change speakers, you do worse.
Well, that is if the model is not adaptive, right? You're speaking of what happens to a static model when the properties of the speaker change.
Right.
Cigarettes, cold, and so on.
Right. So what we do in speech recognition, and we've made a lot of progress in the last few years, is we have built adaptive models. And in this talk, towards the end, I will show you a little bit of adaptation, but it's still of a static nature in the sense I'm adapting to video source. So in principle, if you gave me lots of images with one kind of imaging device and another one with a different imaging device, I have sort of a toehold into where I would go next in order to adapt models built out of the one device to work with another device. So absolutely, that is the goal. And the goal is to do this both with supervised data, a little bit of data from the new source, and also unsupervised. What if I just gave you a completely new source? What would you do? My hope is that there's enough similarity that I can start bootstrapping in an unsupervised way. Yes, that is the goal. We haven't gotten there today, and I won't show you any results where I do completely unsupervised adaptation. But my hope comes from the fact that we've been able to do it in the speech area. And everything I'll show you will be speech models cloned. All right, okay. So adaptation will happen, and it will happen in the third half of the talk. Anyway, so these are the features, and this is typically what they look like in case you want a visual. The LAB moments look like this. If you try to display them, these are the edges that one detects, and this is some sort of co-occurrence matrix saying this image has neighboring correlations which are very high. Right, okay, so these are the features. So here's a little bit of a mathematical formalism. So the HMM says the image I, which is made up of these T image blocks x1 through xt, each of which is like an 80-dimensional vector. It has a likelihood given its caption, or like, and then this probability is essentially the joint probability of the image and the underlying states that the Markov chain went through in producing these T blocks. I just marginalize out the T. So where does the C go? The C goes into restricting the set of states that the Markov chain takes values over. So this is the supervised or the annotated image where we do actually know the caption for the image. Right? And the hope here is that if I see sky in many captions, and in some of them I see grass, and others I see building, I'll have a common density for what the image block might look like given sky. And that hopefully, by some self-organization, this conditional density will try to capture what the sky visually looks like, given that the underlying state is the word sky. And this will tell me what sky appears next to most of the time, maybe other blocks called sky, or maybe other blocks called trees, and so on and so forth. So that's the hope over here. And this is your standard HMM. Yep.
Can you say something about the ordering of those states?
Okay, now the way I've been doing this with the HMM is the states are fully connected, so you can go from any word in the caption to any other word. So at this point, the model doesn't restrict. For example, in alternate blocks, you can go through sky, building, water, and nothing in the model stops it. The hope is that there's enough similarity between sky blocks and building blocks that the self-organization will take over and give it the right thing. Yes. Okay. Oh well, the second line is the same as the first. I guess this is what happens when you prepare a talk. Okay, so in this particular case, we just scan the blocks zigzag left to right. One of the students I'll mention later on is working on a more spatially organized way of going through the blocks, sort of going through adjacent blocks first and so on, even doing region-based traversal of the blocks, but we haven't got any results on that yet. So right now you just go like raster scale. Right. And each density, each image block is modeled as a mixture of Gaussians. Right? This is simply what we had at hand. It seemed to work well. So given a set of training images, you can use standard algorithms, the Bombay algorithm, to estimate these parameters, namely the mu's and the sigmas. And there is, and each particular image, like in each particular concept, has a mixture of Gaussians to model what it sees. So if there are multiple modes, if you have like red evening skies and blue daytime skies and gray cloudy skies, you have a number of Gaussians to play with, so you could hopefully cover all of them by using multiple Gaussians. Okay, so that's sort of the setup, and the number of parameters is basically the number of states, which is the number of concepts you're trying to label, times the number of Gaussians in the mixture for each state, times, of course, these are all vector valued, the x's, so the mu's and the covariances depend on the dimension. So this is sort of the standard model that has been very popular in speech recognition, and some of you are experts. Okay, so what do you do once you have such a model? When you get a new image, you want to know, and this is a standard equation that comes out of this HMM formalism, the probability that you went through some state C. And by the way, what you do for decoding is, if you had 100 concepts in your vocabulary, so that you had 100 HMM states, you create a big HMM where you can go from any of the 100 states to any other. Even though in training you were restricted to going through the 4 or 5 words that the image was labeled with. Now during decoding, you let it go through any of them. And then you get a standard probability out of this model. What is the probability that at time t, time now is like a spatial image block, that at block t, the block t was generated by a underlying concept, sky, or tiger, or tree, or whatever it might be, horse. So this probability comes out of this. So this is all state sequences, all ways of traversing the HMM. If you had 100 words in your vocabulary, then all 100 to the t ways of going through it, which go through the particular word C at time t, or space location t. And this is, of course, just the probability of that whole path, and you sum up all paths which go through C at time t, and this, of course, is the sum of all paths, which is the marginal probability pi, and this simply gives you the posterior probability. And then we say that the probability that the image I contains a concept little c is simply the probability that it went through this concept at some point in the image. Right? So if sky is present anywhere in the image, I want to label it as sky. And the probability that the label sky is good is simply this number. Right? Make sense? All right, so we can also do this, by the way. This sum over all these things can be fairly well approximated by essentially the argmax. Typically, if you have distributions which are very far away from each other, the most likely path has such a high probability compared to everybody else that the sum over all paths is dominated by the biggest term. So you can very often get away from it. So people in speech call this the Viterbi approximation. And by the way, all this thing comes about very efficiently. These computations are very efficient because there's a nice dynamic program that you can write for solving these. Okay. So this is the basic setup. So why did we go into it? Because Pavel and I were working on speech for many years. We knew how to do speech recognition systems. And we knew many other things that one does beyond this. So the first thing is, of course, the HMM design. How many states do you want to have? How many Gaussians do you want to have? How do you want to estimate the Gaussian weight? There's a lot of sort of experience or history behind how this is done. And so we said, okay, let's try to bring all that to bear. Language modeling. When you do speech recognition, you care about what words are likely to follow what other words. So we said, let's try to think about what blocks are likely to follow what other blocks. So maybe sky is not immediately followed by water. Maybe there has to be some ground in between before you get to water, or whatever it might be. Or that if you have seen plane, then the probability of seeing sky is high. But on the other hand, if you have seen, water, the probability of seeing boat might be high and not plane, and so on. So those are the kind of dependencies between the underlying states which the Markov chain captures, and then in a speech recognizer that would happen by way of language modeling. So you'd say, okay, let's see if we can bring some of that. Another little known engineering hack, but which turns out to be interesting in speech recognition, is that the likelihood computed by this HMM and the underlying transition probability of the Markov chain or the language modeling probabilities, they live in very different spaces. So because this is a Gaussian likelihood of a 80-dimensional vector, you get log likelihoods of minus 10 or minus 12, which means e to the minus 12 is the probability of this particular x. Compared to that, you'll get word probabilities of 0.2 and 0.3, and so somehow they don't go very well together. So the standard hack in engineering is flattening the acoustic probability so that you can combine them. So we said, okay, we'll use that. And then this is the point that we were referring to earlier. In speech recognition, we've done a lot of work in adapting a system trained on one set of speakers to a new speaker or new acoustic environment. So we said, okay, let's take a system trained on images from one video source and see if we can adapt it to another video source. So these are the bag of ideas over which I'm going to go in the next 10-15 minutes. I'll knock them off one by one. And if you're more interested in one than other, then interrupt me more in that. Right? So these are the 4 things we've covered. All right. So numbers. There are lots of numbers, so let me just help you go through them. So the first issue was how many Gaussian mixture components should we have? Well, usual empirical. Just try out a few and see what works. And so for the Corel data set, I told you we had 5,000 images which are divided into 4,500 in training and 500 for testing. So in that, it turns out having 10 Gaussians is a good enough. For TREC, we have many more samples to train on, I think something like 40,000 images or something. By the way, we did divide it into a train and test partition even within the 44,000. So this is training on some of them, and you can actually go much higher than 20. You can see it sort of gets good at 20 and goes up a little bit further. The other little trick is that when you're training these Gaussian mixtures, very often the probability, or rather the estimate of the variance of any one Gaussian might become too small. You're starting to overfit. So there's a standard way in speech to control this overfitting. You essentially put a floor on the variance. You say the variance can't get below this. And the variance floor is typically some fraction of the overall variance of the data. So we tried a bunch of them, and sure, having a fairly low variance works well. And those of you who work on speech recognition, compared to speech where this would have been a good number, for images this turns out to be a good number. So these are just details in case somebody really knows this stuff and wants to know. Right? Okay. And so these are the kind of numbers we get. So this is a mean average precision of 0.19. What it means is on average, 20% of the retrieved images actually have what you're looking for. And in case of TREC, it's a little bit lower, it's 17%. And what do we compare them with? Is this good? Is this bad? What is it? Well, like I said, the state of the art when we went into this last summer a year and a half ago, were these 2 things, the machine translation one done by Duigulu and Barnard and Forsyth and so on, and the relevance model done by Lavrenko, Manmatha, and all these things. So one of the nice things about the summer workshop, by the way, is that both these people were there, and we were all working on exactly the same training and test set with exactly the same sort of data that we have. And so it was nice to be able to compare all these things next to each other. So this turned out to be one of the nicer experiences over the summer. And in particular, the machine translation model gets a mean average precision of about 0.15. And so this is considerably better than that. And the relevance model is 0.26. And this is actually a sort of, not quite the model I showed you, but in fact some enhancement of it. So this is clearly much better than this. And these are all the Corel images. So when it comes to state of the art, we're far behind this one, but considerably ahead of this one. Okay, so far so good. On the TREC, the story is a little bit different. It turned out that this TREC task is a whole lot harder. Part of it may be that the video quality is much lower because the Corel images are fairly high resolution. With TREC, you get VHS quality video. So that might be part of it. The other might be, well, that in case of the Corel images, it's very clear. You have pictures of bears, you have pictures of flowers, you have pictures of buildings. In case of TREC, you're looking for cars in regular news footage. You're looking for people. So it tends to be a harder problem just overall. So here, our average precision compared to the MT system is much better. And in fact, we're quite competitive with this CRM system also. So I can claim that we're getting decent results. And of course, is 20% good? Of course not. Like, you get one correct image out of the top 5, 2 out of the top 10. Most people doing search would say that's not good enough. You need at least half a dozen hits in there. So we said, okay, we have to continue working on this. But the good thing is that this already looks good. So if I wanted to show you good results, this is what I would show you. So remember I said this is on the training and test of the 44,000 TREC images that are in-house. So there's also the actual TREC collection of 32,000 images. So on that, we ran these queries. So 11 out of the 17 were states in our HMM, so we could actually retrieve for them. We didn't have labeled data for the other 6. They had things like Madeleine Albright and Samuel L. Jackson, for which we didn't have any labeled images at all. So we just said, forget it, we're not going to evaluate it. And on this portion, our mean average precision is 20%, just as before. And these are the kind of images you get. So the top line is weather news. So all 5 of them happen to be weather news. The second one is horses, and luckily enough, all 5 happen to be horses. Right? The third one is football, and out here, this is actually Andre Agassi playing tennis. But hey, for this system, it's looking at color, texture, this looks like football. And frankly, this is just dumb luck. And I have my own personal guess about why this might have happened. I think there's this funny tinge of blue, which appears only when they create these synthetic maps, which is not there in any other part of the broadcast. So to this system, weather maps, weather news means funny blue in the background. So don't think that these systems are smart and know what's actually happening in the image. They're doing statistical matching. And this happens to be a downward way of matching. These are precision recall curves over here. So the precision stays close to 1 till pretty far into the data set. So we pick up most of the weather images. So that's the nature of this model, if you will. Right? Okay. We looked at modeling these word co-occurrence probabilities. So if I see grass and trees in the image, I'm likely to see tigers. Or the other way around, if I see a tiger, it better be in grass and trees and not in sky and water or buildings or whatever it is. So you would like to model co-occurrence of caption words. So we built a couple of models. One thing we said, forget about them, use uniform transition probabilities. That's case A. Case B, try to model co-occurrence of words in your training captions and build what we call a bigram model. And third, let's just allow captions which are actually seen. In other words, if I've never seen a car, road, and building together, it's not allowed as a possible path through my HMMs. Only paths which I've actually seen in training are allowed. This doesn't mean that my captions coming out will only be captions in the training. Because remember, I do in the end compute posterior probabilities that this image block came out of this particular concept. So, yeah. The previous results from mixed. I think the TREC ones had uniform and the Corel one had this. And you'll see that in a minute because I'll show you results for this with both. So one of them will match up with uniform and the other will match up with bigrams. Right? And this third one, it turns out that this is modeling sort of the totality, like all these things tend to occur together, or don't tend to occur together. The whole caption, all 4, 5, 6 words. Right? So this is sort of a finite state grammar, if you will. And it's a weighted finite state grammar, weighted simply by how often did this configuration of caption words appear in my training. Right? And based on that, you compute posterior probabilities. So it doesn't mean that you will not get probabilities for anything that can happen together. What it will mean is that if you do Viterbi decoding, you'll get only one of the captions that you actually saw in your training. Right? Okay. How does this do? Well, a fair bit better. So remember, I had a 0.193 for the Corel in the last slide. That was with the bigram statistics. So in case of the Corel data, the word co-occurrences improve a lot. So you go up from 0.156 or 0.16 to 0.193. That's like a 20-25% relative improvement. And the reason is that these Corel images are of that sort. So you see polar bear, ice, sky. You see butterfly, trees, grass, flowers. So like, very, very strong themes. So as soon as you know some words, you can find the other things. As soon as you found some objects, you can be dead sure the other object is there, even if there's the faintest visual signature in this really crude set of visual features. Right? So that's the kind of thing you get over here. With TREC, I feel that the concepts are much more scattered. So there's outdoor and buildings, outdoor and mountains. So once you're outdoor, you really don't know whether you're going to see buildings and mountains. So one doesn't really tell you a whole lot about the others. Perhaps building and mountain tell you that it's outdoors, but not the other way. So the correlations are a whole lot weaker. And on TREC, we couldn't get much of a gain by trying to model co-occurrence of these concepts. And even the concepts, they're allegedly organized in some sort of ontology, but we haven't figured out a way of exploiting that ontology or the fact that certain things are special cases or appear with certain other things. And so this is as far as the language model. The next thing we did is scaling of these Gaussian likelihoods. So remember, this was the standard equation. The posterior probability that I went through some state C at time t would be computed like this. All I'm doing is I'm taking this likelihood that comes out of the HMM calculation and flattening it. So k is usually a big number, 2, 5, 10, 20. So you take a very sharp density and you sort of flatten it out. Right? And why do we do this? I have no good answer for it, but it seems to work great in speech recognition. So we said, let's try it over here. And so here's the data set, either the Corel set, which has 375 query words, this is HMM state space size over there, or the TRECVID data set where we had 75 of them. And in this case, I used the full caption or the bigram element because on the previous slide, if you remember, those worked the best. And for the TREC, I just went with the bigram element. And again, there's a substantial improvement in case of the Corel, and this, mind you, is now starting to catch up with the best known result I have for this. So the best known was 0.26 and this is 0.24. And for the TRECVID, again, very small improvements. So I think we have a lot of work still to do over here. So at this point, we decided let's focus on the TREC task. It is definitely the harder of the two. And we went on with that from there. Right? So the next step is adaptation. So a very quick 2-minute tutorial on how speech recognition does adaptation. So remember, this is the Gaussian density model, or the HMM probability, like probability of the image I, given that you're going through some state C, and this is the jth training image. So the way you do HMM training is you do maximum likelihood training. You maximize this likelihood of all the training data. In other words, the mu's and the sigmas are the Gaussian parameters. There's one mean vector for every mixture component of every state. There's one covariance matrix for every mixture component of every state. So there's a whole family of them. And you estimate everything together over all the training images to come up with the maximum likelihood estimates of the HMM parameters. So what you do in MLLR is you say, well, we won't give these models all this freedom of having their own individual means and variances. If I have a good guess of the means and variances from some previous system, I'll simply look at affine transforms of the mean. Right? And in fact, some of the people who just left, they sort of developed this when they were at SRI, and some others at Cambridge, of course. And so now you're just estimating a transformation matrix A and a bias vector B to update the Gaussian means. And so what this means is this model has lots of degrees of freedom to use lots of data. But if I have a little bit of new video from a new source, not enough to retrain my entire HMM, I just estimate the matrices A and B, matrix A and vector B. So this is called MLLR, maximum likelihood linear regression. And the other thing to do is to say, okay, if I don't have a lot of data, I'm worried about overfitting my model, the other thing to do is do something kind of Bayesian. So let's say this probability, the probability that I was in state C at time t in the jth training image, is gamma tj of C. Then how do you normally do the updates of the HMM parameters? It's like just like finding the mean of a bunch of samples. So I saw sample xt coming out of state C with this probability. So there's like a fractional count. So this is the samples that came out of the state times number of samples that came out of the state. Right? So this is like your, it should remind you of the way you usually do estimates of means, right? So this comes out of some HMM calculation, but this is what it is. So what you do in map estimation is you say, okay, let's add tau times a known mean, and let's add a count of tau to the denominator. It's like saying that if I don't have enough samples to estimate the mean, I'll pretend I have seen tau samples of my old mean. So that if I see lots of samples of the new data, it'll overwhelm my old estimate and give you a new one. On the other hand, if I've seen very little data from the system that I'm estimating, for the task that I'm estimating the parameter, I'll kind of default to my old data. Again, these are in case you haven't seen them. If you're an expert in Bayesian inference, this is twice tough. Right? Okay, so we did this for our video data. So we have 13 sources. So we decided to model each of them the way you model a speaker. And we said, this is supervised. So we have 13 individual video sources in our entire collection. And so we went ahead and did this HMM training. So what we did is we sort of built up the HMMs first for everything, like all the images of all the sources for all the concepts. And then we chopped up the data into the 13 individual subsets, one from each source, and re-estimated the HMM parameters on each subset. So now I have a separate recognizer for CNN, and a separate one for ABC, and a separate one for Xinhua News, and a separate one for Al Jazeera, and so on. Right? They're still recognizing the same sort of concepts, but their parameters are now tuned up to a particular source. So here, this was the unadapted system. And by the way, now I've moved over to the 2005 TREC set. That's why the baseline numbers have changed a little bit, as have the number of queries. So the way the 2005 TREC task was set up, there were 39 concepts labeled in all of the training data, of which 10 were known ahead of time to be the ones we'd be evaluated on the test data. So we took the training data, chopped it up into a development and a tuning set, or whatever, training and a development tuning set. And then these are trained on the training set and evaluated on the tuning set of the training data. So again, there's a separation between train and test, but all of this comprises from the NIST's point of view, this was our training data. And they were going to give us a separate test data set later on, in which I'll show you results. So on this one, on all 39 topics or all 39 queries, the average is 23%. The 10 that were going to be evaluated on actually turn out to be a little harder, and you'll see later on why, because you'll see specifically what they are. And on that, it's a little bit lower. But the bottom line is this map adaptation gives you significant improvements in both cases. And by the way, whenever I say significant, I mean both statistically significant under a two-tailed t-test, and also significant in the sense that when you look at the top few images, you can tell that you're getting better images. So both a qualitative feel-like thing and a statistical test. And this one gives you almost no improvement. So it turns out MLLR is too constrained. You do have enough data in each source that you can do more detailed estimation of your parameters. Right? Yeah?
On the previous slide, I thought I saw priors on both means and variances. Is that right? You had,
say that again?
I see means and variances listed here as...
Yeah, but in the results I'm showing you, we only adapted the means. We didn't touch the variances. And we could do it, we just haven't had time to get around to doing it. And in fact, this thing was sent out just end of November or something. When was the deadline going? October, November? Something like that. And then Arnab went on vacation. That's what's doing it well. All right. So yeah, we're getting some gains out of adaptation. All right, good. Next big thing that has happened in speech recognition is people have figured out how to do discriminative training of these hidden Markov models. So the idea is don't just maximize the likelihood of the training data, the annotated images that you see, or the annotated transcribed speech that you see. Try to maximize the likelihood ratio between the speech and its correct transcription and the speech and its most likely wrong transcriptions. So you're trying to find a likelihood ratio criterion to estimate parameters rather than likelihood. People call this maximum mutual information estimation as opposed to maximum likelihood estimation. So and there are papers you can read about. It's all fairly standard by now, right? And so we said, okay, we should do something like that, but instead, like, you know, the training of this HMM parameters using MMI requires a fair bit of code development and so on. And we said, okay, we'll get to it eventually, but for now, let's do something quick and dirty. And what we did is we said, just take all the training images and pick a concept, sky, and set aside the training images that have sky and take the images that don't have sky. Train one HMM with only images having sky, another one with images not having sky. And now the underlying interpretation of the state is no more individual concepts. It's just some hidden variable which helps you model the image. Right? So we've lost that underlying interpretation of the state. But I have two HMMs now for sky, one estimated on images having sky, the other on images not having sky. And then when I get a test image, I simply compute its likelihood under both, and I take a likelihood ratio. And if it's sufficiently high, I say the image has sky, and if it's not, I say it doesn't. And if you want me to rank images based on whether or not they have sky, I rank it based on this likelihood ratio. Right, so that's my retrieval paradigm. So if you want to retrieve images for tiger, you compute all test images for tiger, all test images for a model with no tigers, take the likelihood ratios, sort of that. Right, so that's this new model. And this one, this is sort of a little bit more formalism. So we train up one set of HMMs only from images containing the concept C, another set of HMMs from images not containing the concept C. So the states of this HMM and the states of this HMM now have nothing to do with each other. They're just two different sets of states and Gaussian parameters. And then when we get a test image, we simply compute its likelihood under both these models, take the ratio. And here's the nice part if you care about implementation. Since these marginal probabilities are well approximated by this max, the best path in the HMM, what this means is if I have 100 concepts, I have 200 different HMMs, and I need to calculate the likelihood of a test image under these 200 different HMMs, I don't need to run this 200 different times. What I can do is I can stack up all these HMMs in parallel. So composing HMMs gives you yet another HMM. And then the way you can arrange it is you can do a Viterbi decoding. And there's a version of Viterbi where you can say, give me not the most likely, but the 200 most likely paths. And what you get is you get sort of a path through each of the 200 HMMs. So in one shot, you get all these likelihoods for all concepts, all pairs for all concepts. So the decoding time is just the same as before. Right? Although you're now calculating likelihoods of 2V HMMs. So it comes out pretty fast, and so we're very happy about it. So it scales very nicely. That's one nice thing about it. We can index, I think, the 30,000 or 75,000 keyframes in under an hour, maybe 40 minutes or something. So very scalable stuff. And this, again, seems to work fairly well. So if you remember, these were the numbers for the 39 concepts altogether, or the subset of 10, with the adapted system. Now, there are two different ways of sort of making this discriminative model. One is to just separate the data into two sets of images and train models for each. The other is to train a common model, this is what I say, background in it, and then take the model estimated that way and then retrain them further on the two sets. So if you know HMMs, you know that initialization is sometimes important, and this is another instance of it. So if you initialize more carefully, you get a much bigger jump. Again, another 25% or so improvement in the total performance, and these are sort of our best numbers today. Right? So we've gone a long way. There are a few other things that, oh, yes. Let me do this. Let me go through this very quickly. This is yet another model which another student, Prof, is working on. And he said, we've been ignoring all this audio that goes with this broadcast video. So why do we do that? Let's factor it in. Well, once you have this HMM, now we're not into this discriminative framework anymore. Let's go back to the old one where the underlying states had meaningless concepts. So let's just assume that the image vector as well as a bag of words was emitted by that state. So now you have the image vectors and the word vectors. So each word vector is a bag of words. We do some copy BM25, and I see other people in the audience who are experts at this stuff, so I won't try to tell you how it's done. Essentially, you now have a two observation process, or a pair of observations, or a stream of two observations each, and the underlying states, and the calculation is not a whole lot different. And Brock was able to crank this through, and these are the kind of numbers he gets. So this was the average precision, 0.189 or 188 we had earlier. Adding the text gives him, or gives us a bit of an improvement. Again, this is statistically significant. And so what we're able to do is model both what kinds of image features are seen and what words are being spoken by the news anchor. This, mind you, is ASR output, this is automatic speech recognition. And in case of Chinese and Arabic, it's actually followed by automatic translation. So there's a fair bit of garbage here, but still we're able to get something out of it. And here you can see why this test set is a little bit harder. So there's one concept, prisoner, on which we're completely hopeless. We just can't get it. And part of the reason is like there are very few training examples. That's the sort of statistical or real reason. But even otherwise, it's very hard to tell when a person in the image is a prisoner. It's sort of something very deep. This model has no hope of getting it in the near future, unless you give it a million examples of images with prisoners in them and a million others with people but not prisoners. So anyway. All right. So these are the kind of images you get, and this was on the TRECVID 2005 task. So for building, we got these 5 at the top, and this one is actually the roof of a building. I don't know if you can see it well enough from where you are. And these 4 happen to be buildings. Cars, our model learned that if you have a nice, clear background with some stuff in the middle, it must be a car. So this one happens not to be a car. By the way, we got credit for this because the TREC database, the evaluation is for the whole shot. And this is the keyframe in the shot, but the shot actually had a car in it. So what I'm showing you is sort of a representative keyframe from the video. So don't go by this. This was picked automatically. There was a car in there. So the likelihood of this being high may have been because of one of the other frames in the video. US flag, these 4 are great because they actually have flags in the background. This, I don't know what it is. Sports, we had tremendous precision on sports, 100% till several images. And part of the reason is that these are all from the Chinese source that we have. Again, this must be something to do with the color scheme or something. I don't know what it is. Waterscape, you see both blue sky, red sky, and in fact, dark blue sky and light blue sky. Again, this may have to do with, like I said, don't start hallucinating that this thing is actually understanding the image. It's just doing matching and this clever pattern recognition. Right? Okay. Other results, well, this is a summary. So when we started, what we had at the end of last summer would have given us this on the TREC task. The visual plus text gave a slight improvement, and the discriminative likelihood ratio-based one gave us this. And we were comparing all the while with our colleagues at IBM who had actually helped us bootstrap this research effort. And their best system in 2005, this is by, do I have the name here? I have it somewhere. I think it's Argillander, Iyengar, and Nock from IBM. Their system is out there. So we are starting to beat the people who helped us. All right, so let me just conclude by saying we've had some success applying ideas from speech recognition into this new task. We are getting at, near, exceeding state-of-the-art. I don't want to make very strong claims, because in the latest TREC competition, well, it's not supposed to be a competition. In the latest TREC evaluation, there were a couple of groups from IBM and one from Holland who used all sorts of fancy multi-pass systems with SVMs and who knows what. It'll take me a few months to read all their papers, who got much better than us. So if I showed you 0.22, they have 0.3 or something. So they're a good 25–30% higher. So, but they have all sorts of fancy processing on top of what we do. So anyway, there are many things from speech that we haven't used, and in fact, I said my biggest hope is that we can actually build adaptive systems, which won't require lots of label data of the kind of video or imagery that you want to process. With a few examples, and in the worst case, maybe no examples at all, just a complete bootstrap without the boot, as my colleague Eisen likes to call it. So this is our hope for the future. Thank you. Questions, comments, jokes? All right. Thank you. Yeah, go ahead.
If you were to think about improving the system further, what do you think is the bottleneck? The low-level features or the model itself of the horizontal dependence in the image? Okay,
question is what's more important, the low-level features or the model? I'm a model guy, so I'm going to pay attention only to the model, but I have no illusions that that's where the shoe pinches. The big thing with these things is essentially invariant features. Somebody just asked, what makes sky sky, right? What makes a truck a truck? So we have to have features which are invariant. These features are very, very simple. So other people in my university are working on more fancy features, edge detectors, multi-scale representations, trying to factor out illumination, if you're looking for faces, pose, and this and that. There's a lot of work out there on which I'm not an expert. My attitude is, give me good features. Give me invariant features. Give me features which will be the same value as soon as there's a face in the image, no matter whether it's well lit or dark, or whether it's facing upside down or tilted. And if you can give me that, I can find the face. And of course, you're going to say that's easy. But no, I think there's a fair bit of modeling left on top of it, because these features will always be noisy. And we'll have to make inferences essentially from noisy data. So the modeling part takes care of that. And there's a fair bit of work, which might go hand in hand with the model mind. It doesn't have to be compartmentalized. So the answer is both. I have a timeout from I'll take questions now, whatever, offline, and we can decide.